Okay, so exponential functions. That is a function in which the independent variable, and typically our independent variable is the x value. The input value is typically x. It can be called something else, like another kind of typical one in exponential functions is t for time. But usually when we talk about an exponential function and its independent variable, it will be typically x, and it will appear in an exponent. So the x value is in the exponent of the function. Let's circle this right here. It has this form, f of x equals, f of x is the same as what again? Y. So f of x or y equals a times b to the x power. Now notice the a isn't in parentheses with the b, it's just the b that is being raised to the x power, and then there's a multiplier of a out front. So a can't equal 0, because what would happen if we multiplied that b to the x power by 0? We'd have 0, our exponential function would be gone. B cannot equal 1. B is what is being raised to the x power. What happens when you raise 1 to a power? It just stays at 1. Would anything be happening on the graph? No, we'd end up with a linear function. We would end up with a vertical line. Not a vertical line, a horizontal line, excuse me, instead of a exponential function. And b is going to be greater than 0, or in other words, b is going to be a positive multiplier. So, an exponential function does not have a common difference. What kind of functions have a common difference? We talked about yesterday. What kind of functions have arithmetic sequences which are related to which family of functions? Which family of functions is modeled by an arithmetic sequence? The linear family. So the linear family is the one that has the common difference, but instead this one has, just like our geometric sequences do, it has a constant ratio. So there's a constant ratio happening between the y values, just like in our geometric sequence we had a constant ratio happening between our terms. And that constant ratio is the value of the b in the model. So the b that is being raised to the x power is that constant ratio. So to evaluate an exponential function, one of the places students have the most trouble and they end up with getting it wrong is because they forget to follow order of operations. Make sure you follow order of operations. And don't get mad at your calculator if it doesn't do it for you properly. So you got to make sure that you understand what's going on. Okay? So let's do some evaluating of exponential functions. Let's go to page 628. And this is problem number 2, it says. So we have the function f of x equals 50,000 times 0.975 being raised to the x power. This is really important that we always pay attention to this part of the reading in these word problems also. So tell me what it says next. Where x what?
Represents the underwater depth in meters.
Where x represents the underwater depth in meters. So that x in the exponent is saying how far under the water are you in meters. And the function itself, or in other words, the y value, models the intensity of light below the water surface in lumens per square meter. So we always need to make sure we understand what the x and the y are representing. So what's x again?
Meters.
Meters underwater, right? The depth of it, how far are you underneath the surface of the water in meters? And what's the y representing?
The intensity.
The intensity of the light in lumens per square meter. Okay, so we're supposed to find the intensity of the light. So what are we looking for, x or y?
Y.
Is Austin the only one alive today? if we're looking for the intensity of the light, we always have to make sure we know what we are looking for. Are we looking for the X or are we looking for the Y? So we would be looking for the what? If we're looking for what is the intensity of light, are we looking for the X or the Y? The Y value, 200 meters below the surface. What's that 200 then?
Yeah.
The X value. So it says, and round your answer to the nearest whole number. So we're going to, let's just change our f of x to y. We are looking for the y value, the intensity of the light, given that this function will find it for us if we know the meters. So what are we going to put in for x? 200. Okay. How would you like to have to do that one without a calculator? No. Okay, let's see if you can figure out the answer for this one. And what it is, rounded, it said to the nearest whole number.
$316.
316, Andrew says?
Point what?
It's just rounded number, right?
Oh, yeah.
If it's rounded to the nearest whole number, is 316 correct then?
Yeah.
Okay, so we're going to say y is approximately equal to show that we had to round, 316, and what would the label on that be?
Lumens per square
Lumens per square
meter.
meter. And I don't know the abbreviation for lumens, so we're just going to write it out. They didn't show us what the abbreviation for lumens is, and I don't know it. Or it could be lumens per meters squared. It could also be written with, this one down here could be meters squared like that instead. Okay? Okay, now did anybody have trouble getting that?
No.
Did that work on your calculator? Okay. So I want us to make this note, though, in our notes, that we make sure that if for some reason we're doing it in a two-step process instead of a one-step process, that let's put a little star here like this and say the 0.9575 has to be raised to the 200th power first. So let's make sure that we understand that if we're going to do it in a two-step process, we don't do this. Take the 50,000 times the 0.975, see what that is, and then raise that to the 200th power. In fact, would you try that? Let's just do it. Do a two-step process. You get what? Overflow error? Oh yeah, because 50,000 times just almost 1 would be 50,000. Now 50,000 being multiplied by itself 200 times. Yeah, your calculator doesn't like that, does it? Anybody's calculator like it? Putting it into at least scientific notation for you or anything? No? Okay. So make sure that we understand how to follow order of operations and or make sure that our calculator is following order of operations, okay? So
Wait, mine, I'm confused because mine did the opposite.
you just did it?
Yeah, I'm confused.
Well, that's because you're just following order of operations here. So I wanted you just to take 50,000 times the 0.975, stop, and just hit enter, and then take that answer to the 200th power. That's what I want you to try. Okay. Okay, let's go to 629, page 629, number 36. Let's do another one of these, evaluating exponential functions. Number 36. As a promotion, a clothing store draws the name of one of its customers each week. The prize is a coupon for the store. If the winner is not present at the drawing, he or she cannot claim the prize, and the amount of the coupon increases for the following week's drawing. So the function f of x equals 20 times 1.2 raised to the x power gives the amount of the coupon in dollars after x week of the prize going unclaimed. Okay, I want us to evaluate that function though first of all. I mean, just tear it apart and say, what's going on in that function? Where did they get those numbers? Or at least, what is the A value in that function? The 20. And what is 20 in this case, do you suppose? What do you think the 20 represents? Any ideas? The starting amount, maybe. In other words, if it's the starting amount, that would be, what is X representing in this problem?
The number of weeks after.
Okay, the number of weeks, okay. The number of weeks after the drawing. Okay, so then what's the Y representing? The M of X?
Would be the amount of money.
The amount that the coupon is worth. So if $20 is the amount of the coupon, what's 1.2 raised to the 0 power? So at the start, 0 power. What would 1.2 to the 0 power be?
0.
No.
No.
1.2.
It's 1.
1. Anything to the 0 power is 1. So then now we'd be taking that A value of 20 times 1. What's 20 times 1? 1. 20. Not 1. 20, right? Okay, so it appears that the coupon starts out at $20. Okay, I wonder where the 1.2, what the 1.2 tells us. Where did that come from? I wonder what that's about. Well, let's start answering the questions and see if we can figure it out as we're going along. A, what is the amount of the coupon after 2 weeks of the prize going unclaimed? So the first thing we're going to do is write down our function. So f of x equals 20 times 1 2/10 raised to the x power. So that 1 2/10 is which value in our function? Well, there's only the A, B, the B. Yeah, the common ratio, the constant ratio. So we can change this to y. We have 20 times 1.2. Oh, maybe we're looking for y. I don't know. Which one are we looking for? Are we looking for the coupon amount or the number of weeks?
No, the coupon. Wait.
Amount of the,
Yeah.
The amount of the coupon. So is that our y or our x?
That's why.
That's y. Okay, well then, what are we going to put in for x? 2, because it's after 2 weeks, right? So now go ahead and figure out what that is. Well, let's see. It doesn't tell us what to do. Does it say what to round it to?
No.
Okay, if it doesn't, then we use our common sense and say, what is this y representing? Money. Okay, so how do we typically round money then? To the nearest dollar or to the nearest cent? The nearest hundred, right? Okay, so rounding to the nearest cent, which would be the nearest hundred. $28.80. Okay, $28.80 is the value of the coupon after 2 weeks. Okay, that was the question asked. B, how many weeks of the after how many weeks of the prize going unclaimed will the amount of the coupon be greater than $100? Okay, so now we're to part B. So we have this y equals 20 times 1 point, oopsie, didn't write that correctly. 1.2 raised to the x power. And the question is, after how many weeks will the coupon be greater than $100? So are we looking for x or y? Now we're looking for x. Okay, well then that means we're going to put the 100, but it's got to be greater than 100, right? So that would be $100 and 1 cent. Okay, so it's got to be at least $100 and a penny. Okay, well here's the deal. To solve that, to be able to get x out of an exponent, we're not going to learn how to do that this year. That is called logarithms. You have to take the log of each side to get the x out of there, and we're not going to learn that this year. They're going to learn that in your next algebra class. So all we can do is keep trying with our calculator different values for x until we get there. So we already know it's more than 2 weeks, right? Okay, start trying. Start playing around. Start at whatever number you want and go up or go down from there and figure out what x is going to have to be.
It's less than 10.
It's less than 10? Okay, Devin's already decided it's less than 10, you guys. He's convinced. I don't know how he's convinced, but. Is 10 over $100?
It's 123.
Yeah.
123.
Now it's
Yeah.
103.
It's
9
9.
is 103?
Yeah.
No.
Oh, 8.
8 is like 85.
Oh, well then it's gonna be after
Like 8.5.
9, well, no, they don't do it in halves, they say, somebody claims it, they draw the next week, so after 9 weeks, if it goes unclaimed for 9 weeks, so X is going to equal 9 weeks. So that was the question, 9 weeks, it will be greater than $100. Okay. Answer C says, what is the original amount of the coupon? We already talked about that, didn't we? What is it? $20. We said the A value is the starting amount. Hear me on that. In an exponential function, the A value is the starting amount. So what did we say? You would put 0 in for X, and you would take that, 1.2 to the 0 power, and you would get 1. And then when you take 1 times 20, you'd get 20. What ordered pair would this be? If I did tell you to start graphing this, 120? What did we just say X was equal to? 0. So this wouldn't be ordered pair of 120, it would be ordered pair 0, 20. So on a graph, it's important that we understand that the starting amount is going to be the what then? What's that called, that 0, 20? The y-intercept. It's going to be the y-intercept, where x is equal to 0, what's the y value? So these are kind of important things for you when you're going to have to do some of your homework today. You need the y-intercept to be able to tell the starting amount, to be able to, and that's just your a value, isn't it? Do you think it would matter what b is if you raise it to the 0 power?
No.
Would you still get the a? So I don't care what you make b, if you raise it to the 0 power, and remember b can't be 0, it has to be, it can't be 1, well it couldn't be 0 either because, so what, it has to be greater than 0, b has to be, so if b is greater than 0, any number greater than 0 raised to the 0 power will be 1, and 1 times a will be a, so is a always our starting amount? Yes, a will always be our starting amount. Okay, part D. In part D it says we need to find the percent of increase each week.
I think that'd be B.
We think it would be B, okay? So the B might help lead us to it, right? So the amount of the coupon keeps increasing, doesn't it? So it keeps going up, then up, then up. As we go across the x-axis, this exponential function keeps climbing. So there's a percent of increase going on. Well, I'm going to tell you that it is the B value that we're going to look at. B equals 1 2/10, which 1 2/10, we need to change that to a percent. What percent would 1 2/10 be? 120%. Well, if that's 120%, they're saying that 120% of the starting amount is what's happening when it's being raised to the x power. So does that mean there's a 120% increase? Well, how much increase would there be? What's the 100% talking about? It would be a 20% increase because the 100% is what you have. It's the whole that you start with. And that 1 changed to a percent would be 100%, and so that 100% is what we actually have, and it increases the 0.2, the 20%. So that 20% right here, this is our percent of increase. %20 increase each week. The value of it increases another 20% each week. So it takes its value that it is at that time, maybe it's that $28.80 after the second week, and it multiplies it by 1.2 because it wants to still keep the value of $28.80, but now it also wants to increase it another 20%. So would you find out for me what is 20% of $28.80, please? What is 20% of $28.80? Should get $5.76.
Yeah.
Do you?
Yeah.
You gotta take it times 0.2, don't you? Okay, $5.76. Add $5.76 to $28.80. What do you get?
34.56.
Okay, I'm just gonna put that there just so we have it to look at. Now I want you to take our exponential function 20 times 1.2 raised to the third power, because we just did another week. We just added on another week without using the function. So what is 20 times 1.2 raised to the third power? Well, isn't that something? Okay, $34.56. So the 100% says keep the value of the coupon as it is right now. That's the $28.80. Add on another 20% of that $28.80, which we said was $5.76, and now the coupon is worth this. So the next time it calculates it, it's going to take that $34.56 and take 20% of it and add that onto it, and so that's where the 100 comes in. It's taking the coupon value at that time, adding on another 20% to that coupon value, not just 20% of $20 every time. Okay, let's go to the back side, where we now determine if we have exponential functions or not, and if we do, we're going to learn how to write the equations for them. So to determine if a set of ordered pairs satisfies an exponential function, we're going to look for, just like we did yesterday, a constant ratio, or a common ratio, if you'd rather call it that. And it's going to be in the y values, are the y values. So we would take a y value divided by its previous y value, take another y value divided by its previous y value, where there is a constant change in x. If it does, then we're going to write the function that we know the model for. And what did we say a is going to be? Starting amount. What does it start at? At x equals 0. What's your y value? And what's our b value? The constant ratio. Yep, b is our constant ratio that we're going to find. Okay, so it looks like we're going to do number 3 on page 628. We have the set of ordered pairs given to us as in set notation. Let's write them into a table. It makes it easier to work with them. Okay, so go ahead and get those transferred into my table I have here on the notes for you. Okay, so we are first of all needing to determine if it is exponential or not before we even try to write an exponential equation. No sense writing an equation until we know if it's exponential or not. So we're going to start with, just like we did in our geometric sequence, do we have a constant change going on in the x's? They're going, what's happening?
It's going up.
They're going up by 1. So as long as you have a constant change, wherever there is a constant change in the x's, now you can check out to see if there's a constant ratio. Well, we got a constant change going on all the way through our x's. So let's start with -4 and divide it by its previous term, which is -1. What's that? 4. Okay, I need to move over a little bit or I'm going to get into my next problem's territory here. -4 divided by -1 equals 4. Okay, now we're going to take the -1 and we're going to divide it by its previous term, which is 0. What is that? No. No way. It's not 0. Okay, try it on your calculator because it's 0. Your calculator. Can we divide by 0? No, it's undefined. Okay, well then we'll take the 0 and we'll divide it by its previous term, which is -1. What's that? 0. Well, does it look like we're getting a constant ratio? No. So this is not exponential. So that was the question. Do these set of ordered pairs represent an exponential function? It's not exponential because we could not find a constant ratio and our work supports it. But I'm going to challenge you to that you should be able to tell me what kind of function this looks like it might be just by looking at those x and y values. What's a possibility of what it could be? Josh, what's that? What are you doing? Or why do you have to do it down there then where I can't see? Okay. Then why could you, or what am I asking you to do right now? Look at the table and see if you can predict what kind of function this might be. Come on guys, you can do this. Let me help you out a little bit. Is it linear? Is there a constant difference, a common difference going on in the y's? No, they're not changing by a common difference or a constant difference, so it can't be linear. Makes the parabola. What's that called?
Quadratic.
Quadratic. Doesn't it kind of look like there might be some symmetry happening here?
Yeah.
Right here and right here? Oh, it's very possible then that this maybe when x is -2, y would be what? When x is -2, y would be the same thing. If it's quadratic, what would it be?
6.
Negative, oh, you guys. If we put -2 in the table, it probably would be -4 if this is quadratic. So it's a little bit more like that one might be a quadratic function. Okay, let's do transfer 4s to a table. You get 4s ordered pairs in the table. After they are in the table, make sure that you have wherever there's a constant change going on in the x's, we can check the y's. Looks like the x's are always increasing by 1, so we can check all of the y ratios.
Yeah, this looks.
So we're going to do 64 over 16, what's that? 4. 4? Okay. And 16 over 4 is 4, and 4 over 1, of course, is 4. So we do have a constant ratio. What's that in a geometric sequence? We would call that what? R. In an exponential function, we call it b. So we just found our b value. b equals 4. Because if it is exponential, we're going to write the exponential function for it, just like it says up here over on the board for our homework. In 21 through 24, for the 2 yes ones, there's going to be 2 that are yes in those 4 problems, and 2 that are no. For the 2 yes ones, I want you also to write the equation, the exponential function for it. So that's what we're going to do right now. We're going to say, what would our y equals ab to the x power look like? So we need to replace the a and the b. Well, we already know the b, don't we? Okay, so it's gonna be y equals something here for a, 4 raised to the x power. We just need the a value. What's our a value? The starting amount, the y-intercept. It's 1, isn't it? Because here's our y-intercept right here. You might want to put that in your notes too. That is the y-intercept, and the y-intercept is our a value, so a equals 1. The y value when x is 0 is our a value. So 1, well, that's not how we're going to see it written. It's going to get cleaned up because 1 times anything is the same thing. So we're going to just, oopsie, I wanted an eraser, not
It's
that.
just 4 to the x.
So it's going to be y equals 4 to the x power. We can just write it like this. There you go, there's our equation. Y equals 4 to the x power. We would have understood that the multiplier, the a value, would have been 1 because multiplying by 1 is kept invisible. Okay, let's do one more. Okay, I have a set of ordered pairs here for us to put in the table. It appears the x's are going up by 1s. By the way, they don't have to go by 1s. They can go by 2s. They can whatever, but they have a constant change. And then let's check out your ratios. Negative 24 over negative 12. Negative 12
Goes up by
over negative 6. And negative 6 over negative 3. What do all those divide out to?
2.
Positive 2?
Yeah.
Okay. That's good because it said our b value should be what? Positive. It should be positive. So this is our b value. So this is exponential. And b equals 4. So now what we need is our a value. What's our a value?
Negative 3.
Negative 3.
How does B equal 4?
Yeah, that's what I'm,
Oh.
yeah.
Why did I raise 4?
I was
Yeah, I don't know either. I should know that when somebody out there, or more than somebody, has a strange look on their face, I must have done something wrong. Okay, b equals 2. What does our a equal?
Negative.
And how do we know that?
Because that's our starting.
It's the y-intercept. It's right here in our table. When x is equal to 0, the y value is the y-intercept, and that makes it our starting amount. So our equation would be y equals negative 3, the a value, times 2 raised to the x power. That's how we would see it written. Okay. So if it is exponential, we are going to write we're going to practice writing the exponential function for it also. Okay. Now, what if they did not give us the 0 in our set of ordered pairs? How would we find the y-intercept then? Because we don't have the function to plug it into. So what if this table instead had started at 1 and went like this? We'd have negative 6, negative 12, negative 24, and negative 48, that would be, wouldn't it? Keep multiplying by 2 going this direction. This direction we multiply. Well then, how would we figure out what
Just
we would do the undoing? We would divide by 2. We would say, oh, well then, if we go back a unit, then we would be at x equals 0, and if we're going backwards, we have to divide, so that would be a negative 3. So just because the table doesn't have the y-intercept in it, doesn't mean you can't write the function. It just means you have to work a little harder, okay? So questions on any of this? Okay, it's a book assignment, so you get to work on it. I don't have anything to hand out to you then. You have what you need.